Okay, looks like we're live on Facebook. All right. Fantastic. Okay. All right, so we'll give people a minute more just to log in, and then we can get started pretty soon. Excellent. All right. All right. So we're at 5:31, and I can start with introducing the event. So thank you everyone who's logging in tonight, who's viewing from the Zoom link on our library homepage, or who's viewing through Facebook. Welcome to Popping the Science Bubble. We are so glad to have this collaboration back. Berkeley Public Library has really enjoyed working with UC Berkeley students and graduate students and postdocs over the years to make Popping the Science Bubble happen. And we're just so happy that the Popping the Science Bubble team have come back. Popping the Science Bubble is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic they find really interesting. The organizers are 3 graduate students at UC Berkeley, Jenna, Madison, and Oksana. If you're interested in checking out their past seminars, you can visit their website, check out their Twitter or Facebook, and sign up for the listserv to keep in the loop for upcoming seminars. Our speakers shared additional interesting resources if you want to learn more about any of these topics discussed today. You can view these at their website. Thank you. And now I'm going to hand it over to Jenna, Madison, and Oksana to introduce tonight's speakers. Thank you.
Okay, great. Thanks, Kelsey, for helping us get everything set up virtually. So before we begin, we just want to say we encourage everyone to ask questions during the presentations because we want to have a conversation. So Madison, Oksana, and I will be monitoring the chats both on Zoom and Facebook, and we'll ask the speakers the questions as they appear as time permits. If we can't get to your questions in the moment, or if you have additional questions after the talks, there will be time at the end of both talks to ask away as many questions as you'd like. So with that, let's get started with our first speaker, Justin.
So our first speaker is Justin Ondry, who received his PhD in physical chemistry from UC Berkeley in 2020, where he studied atomic scale defects in nanocrystals under the guidance of Professor Paul Olivisatos. Prior to that, he received his BS in chemistry and material science in 2015 from UCLA. In his free time, Justin enjoys skiing, backpacking, and caring for his ever-growing plant collection. Take it away, Justin.
Thank you for that wonderful introduction. So I'm Justin, and I just received my PhD a few months ago from UC Berkeley. And I'm going to tell you a little bit about how, as scientists, we actually see atoms using electron microscopes. And hopefully I'll show you some really beautiful images today. And as the organizer said, please ask questions. I love answering them. So to begin with this, what I first want to get the idea across is how small atoms are and how close together they are. So if I was giving this presentation to a person, you'd realize that I'm actually quite tall, about 2 meters tall. And so we're going to use that as kind of a ruler for how close together atoms are. So if we start and we go smaller, we know that atoms are somewhere around 2 angstroms apart. If you're not familiar with that, that's 2 × 10⁻⁻10 meters. So that's 10 orders of magnitude smaller than I am. For those of us who might be more familiar with inches, that's a very small number of inches. And so as an example of this, in diamond, a material that maybe some of us have around our fingers, the carbon atoms in diamond are 1.54 angstroms apart from each other. So now kind of use that as a gauge of thinking about how small these little atoms are and how close together they are. And one way I like to think about this is let's go an equal amount bigger than I am to really put this into perspective. So that would be somewhere about 20 billion meters, or 2 times 10 to the 10 meters, which would be about 12 million miles. How big is that? That's 1/7 of the distance between the Earth and the Sun, or about 500 times around the circumference of the Earth. So think about how long of a distance that is, and how minuscule I am, or all of us are, compared to that distance. And that's how much smaller atoms are than we are. So I hope this at least gives us some perspective of how tiny the atoms are in materials. And I've been doing research on this for 5 years in this world, and I still don't really understand how small these things are, but they are very small. And now the question is, can we see that? Can we see 2 atoms separated in a material? And so you might ask, well, like we're familiar with from high school biology, we might have used a light microscope. And we might ask the question, can we use a light microscope to see the 2 separated atoms in a material? And so the first thing I want to get, concept that I want to introduce is this idea of resolution. So resolution is the ability of seeing that 2 things are separated, being able to actually see that they're separate. So an example that we may be familiar with is the headlights of a car. If we see a car very far away, we may see one blob of light, but we know that there's actually 2 headlights on a car. Hopefully not one of them's not burnt out. And as we get closer, we'll get to the point where we can actually see these 2 headlights as individual entities. So when we can actually see these 2 things as separate sources of light, we say that those have been resolved. And so the question that we want to ask is, could we resolve 2 atoms that are 2 angstroms apart from each other with a light microscope? And if you do microscopy, there's this one equation. This is the only equation I'm going to show you today that I want you to take away from this, is the resolution of a light microscope depends on some constant times the wavelength of light that you use divided by the numerical aperture. And this numerical aperture is about 1 for our purposes. And so the resolution of the ability of a microscope to see whether or not something is 2 things rather than 1 depends on the wavelength of light. And so typical light that we work with, that is all around us, is about 500 nanometers. So you plug that into this equation. What that means is that the resolving power of a typical optical microscope is right around 300 nanometers, or 3,000 angstroms. This is without playing any fancy tricks or anything. And more or less, the technology of a light microscope being able to resolve things was perfected, and this type of resolution was achieved in like the 1890s. And since then, there hasn't really been, other than super resolution techniques, hasn't been a huge advancement there. And so all of this comes down to, you may remember from high school, the wave nature of light. We've heard that light is a wave and a particle, and all of this comes down to the fact that these are waves. And a wave basically undergoes what's called diffraction or interference. So basically, if you have a little slit, what will happen is this will create an interference pattern where you'll have a peak, but then also all these interesting little waves or intensity variations, essentially. And this diffraction, this is what limits a microscope's ability to resolve 2 tiny objects and whether or not they're next to each other. And so if we were doing this in person, I would actually show you an example of live that a light behaves like a wave. because I have this little diffraction grating here, and I could shine my laser pointer on it, again, if we were doing this in person, and you see basically the light reflected. You see a main intensity one, but you see all of these little intensity variations, and all of that comes from the wave nature of that light. And similarly, I'm shining my laser pointer on this diffraction grating, and we see a bunch of different peaks in intensity. And that's for scientists a way that we can tell if something is behaving like a wave. So now I'm going to step back and ask, well, what if we use something else to do the imaging? Instead of using light, what if we used an electron? And so an electron is just this little charged particle by itself, and we can accelerate it and use it kind of like light. And in 1927, what some scientists figured out was that a beam of electrons also behaves like a wave. And it's really hard to see in this image, but what this image is showing is different intensity fluctuations coming from the electrons diffracting rather than the light diffracting. It's a little bit easier to see in this other exciting example where we have these intensity fluctuations of the electrons getting reflected from a crystal. And so this is showing that, okay, these electrons also behave like waves, and they're going to be limited by the same physics of a light microscope, but maybe the wavelength's different, and that will help us. And so what I want to get across to you here is that electrons also behave like waves. And in 1937, these gentlemen were awarded the Nobel Prize in Physics for showing that. And then what happened was, or what people realized is that if we go back to this resolution equation that I hope you're okay with, is if we now plug in the constants for an electron, what would happen? Now, the difference here is that the typical wavelength of an electron that one is able to use for imaging is 0.003 nanometers. And so if we plug that in, what we see is that now the resolving power of a microscope, if we get everything perfect, will be 0.015 angstroms. So I'm going to ask you a rhetorical question. Don't try to answer this by unmuting yourself. Could we resolve a pair of atoms with using electrons to image them based on this equation? I'll give you a second to think about that. And I'll remind you, in the first slide, I told you that typical atomic spacing in a material is around 2 angstroms. So I hope you came up with the answer is yes. In theory, we could. And if not, that's okay. And so some people had this, they kind of looked at this physics and they said, okay, well, what if we tried to actually implement a microscope? And in 1931, they built the first electron microscope. It was eventually awarded the Nobel Prize in 1986 for that discovery. And what they realized is that the first electron microscope was way worse than a light microscope. And there were all kinds of problems in being able to do that. But, and I'm not going to walk you through the almost 90 years of technical developments that has led to the modern electron microscopy. But today, scientists have access to incredibly powerful electron microscopes. Engineers have ironed out a bunch of bugs with the way we form electrons, with the lenses that we use to image with electrons, the detectors, all of these things. And right now we can achieve 0.5 angstrom resolution. So that's, we can easily see individual atoms in a material using one of these microscopes. And I just want to highlight for you, these systems are so sensitive and so beautifully engineered that a human being just being in the same room as one of these microscopes the heat from my body messes up the electronics such that the microscope has its room and the people have its own other room over here. And it's operated entirely remotely. And on the inside, it's a mess, I must say. All of this sensitive electronics, I don't know how many miles of wire, but it's a lot. All of that has enabled what I'm hopefully going to show you now is some really exciting images that most of which I have not collected. This is just what others have done. It's really, really fascinating. So the first one, the easiest example that I want to show you is images of graphene. So we may have heard about graphene as this really exciting new material with wondrous properties. And what graphene looks like on an atomic level is these honeycomb lattices of carbon atoms. And that's exactly what these authors down here are able to observe. You see each one of these bright white dots is that carbon atom in the material. So we see that beautiful honeycomb lattice here. Now you may ask, well, what's going on up here? And what's going on up here is the two layers of graphene are stacked on top of each other. And they don't stack on top of each other where one carbon atom is directly on top of the next one. They actually are slightly offset. So for example, we see these brighter areas here. Those are actually where two carbon atoms end up on top of each other, whereas these other areas here where there's one atom and they're offset from each other. So this is a really cool example, but it actually shows one of the limitations of these electron microscopes, and that's that we're looking at a two-dimensional projection of the image. So think of it like if I had a light bulb and I had a shape and I was creating a shadow of it. If I put a sphere or a rectangle or a cylinder there, depending on, I may end up in a situation where I've identified a cylinder and a sphere as the same thing because of the way their shadows look. But what we know that you can do is if you want to determine the three-dimensional shape of something, what you're going to do is you're going to look at it and then you're going to rotate it around to get an idea of what it looks like. And that's exactly what you can do in one of these microscopes. And so what I'm going to show you here.
Hey, Justin, sorry, a quick question.
Yeah, of course.
Why do the atoms appear as white spots? And what are the dark spots then?
So all of this, we never actually see electrons. Our eyes are not able to see them. So what we're doing is we're interpreting that signal. So with this image, basically, we're looking at places where the electron beam has been scattered more. And we're actually, in this case, we're collecting the scattered electron signal. So where there's an atom, if the beam is hitting it, we're seeing more scattered intensity. And then a detector measures that scattered intensity as a current, essentially. And then this image is actually just a kind of not computer rendering, but each pixel in the image is how much current is hitting the detector at that position as we're scanning the beam across. I hope that answers your question.
Yeah, cool, thank you.
Cool. That's a great question. And there's actually a ton of different ways that we see electrons. We could do a whole nother seminar on that. It's a fascinating question. So back to where we were. With these taking a sample and rotating it around, we can use all of those kind of two-dimensional images and use the computer to put back together the three-dimensional structure. And so what these authors here did is they took a tiny iron platinum nanocrystal. So it's a tiny little, maybe 20 nanometer sized crystal of iron platinum. And these are really important for computer data storage, for example. All of our hard drives have these little iron platinum crystals in them. And what they did is they took like 100 images as they rotated this particle around inside the microscope. And then they developed a piece of software that puts that all back together, and we can figure out the three-dimensional structure. And this is what it looks like here. Each one of these dots is an atom of iron and platinum. I believe the red is iron and the blue is platinum. And they were able to take this nanocrystal, actually take it apart and look at all of the different heterogeneity in the sample. And what they determined is that there's actually two subdomains in this particle that are kind of fused together. And they're not, each domain is not quite like the other. And then there's these like disordered domains kind of in the middle. So we're kind of taking apart this nanocrystal. We can really understand where the atoms are and what's going on inside. And these knowing where the atoms are, that's the key to understanding how these materials might behave or what the properties might be for some sort of application. Okay, so I've shown, yeah, go ahead.
Another question for you, Justin.
Yeah.
So how is it possible to manipulate a nanocrystal? Isn't this really small?
Yeah, that's an excellent question. So I will say it's very difficult. The authors who did this work, it took them like 10 years to develop all the pieces so they were stable enough to do this. But basically, what we have is we have this little nanocrystal. It's on a support of something that's relatively transparent to electrons. And then, so that nanocrystal is in some part of the support. We can take images there. But this whole support is connected to a big rod. And this big, imagine my arm is that big rod. And then this rod we can rotate this way and change the height and all of that. And so and it's all controlled actually by little motors, but through geometric reduction of the gears and stuff, we're able to make tiny rotations of a little nanocrystal in that way.
Wow, it's really cool. I was imagining super tiny tweezers or something. That's the only thing I could imagine.
Cool. Yeah, another great question. And those were part of the 90 years of technical developments that I kind of glossed over. Each one of those was critical for making this happen.
We have a question from the audience, from Joseph. So his question is, if atoms are in constant motion due to heat energy, why isn't the image blurred?
Oh, that's a great question. So yes, they are in constant motion, but every atom has a place that it's allowed to be in a crystal, and it moves within that position, but it never jumps outside of where it is. So it has a little corral of space that it can be in. And so when we take one of these images, we're actually averaging over all the positions that one atom has in its case, or it's accessible to it. But yes, for example, if we looked at a gas in one of these microscopes, the atoms are moving all over the place. And so that would be, you wouldn't see any atoms. It would be a blurry mess. But yeah, excellent question. Thank you. So in case the video was too much for you, I just put one of the figures from their paper in here showing all of these different subdomains of the particles and the way the iron and the platinum are kind of ordered in this material. All right, so now, another place where electron microscopy has had a huge impact, which is a place where I'm not as familiar with, but I think it's worth going through and showing you, is the world of structural biology. So in addition to finding out the structures of materials, these tools are also used to figure out the structures of cells and proteins within cells. So you've opened up a textbook in biology in high school maybe, and you're like, well, how do they know what a cell actually looks like? Or how do they know what this protein looks like? And a lot of times it was figured out using an electron microscope. So using the same ideas of taking lots of images of something as it's rotated around, they can determine the structure of things like proteins. So this is an example of the ribosome, which translates DNA into the other proteins that make our whole bodies work. It's a huge molecule. But within these structures, they can actually determine kind of with atomic resolution where the different amino acids are and how they're contorted within here. And so you can imagine how powerful this is from both from understanding how cells work and how biological pathways work, but also from an engineering standpoint. If you identify this protein as doing something bad to your body, they can get the structure of it and then figure out, well, I should put this molecule in and that'll inactivate it. And they know where in this molecule there's places where you can bind a protein or another protein or a small molecule or something like that. And so this has been almost a revolution in the structural biology world. And I'm going to end with this in showing a very relevant example. We've all seen this rendering of the coronavirus from the FDA. They put it all over the place on every little handout you could get. And this is more or less a rendering based on TEM characterization of one of these virus molecules. So to show you a timeline of what this was looking like kind of in the literature as it was coming out, in around January, they were taking kind of these low resolution images of these viruses and saying, oh, look, this person's sick. We see these viruses in them that we don't know what it is. But we see it's this round blob and there's these little spikes on it. That's where that coronavirus name comes from. And they had some images of the spike and they're like, oh, this is related to this virus that we know about. And that was, this is like, less than a month after these issues were starting to come out. But 2 months later, I showed you that example of the ribosome. This protein on the surface that is the key to like these viruses being able to infect human cells. A group at UT Austin had fully reconstructed with near atomic resolution the structure of that protein. And so this structure is what all these companies and groups trying to develop vaccines are looking at. They're like, how do we trick their cells into figuring out that this is a bad person or a bad virus, and we don't want to let it in. And so I think this hopefully really highlights to you how all of these really cool tools that we have are hopefully going to have a very positive impact on human health in the near future. And then I'm going to end with, what do I do with an electron microscope? None of the stuff I showed you today I did or was even remotely involved in. But I thought it was some of the really cool examples to show in a talk like this. But yeah, so this is me in front of my electron microscope. And this green glow here is basically the electron beam hitting what we call a phosphor, which basically electrons hit it and it converts the electron into a visible light that we can see. So you're really seeing kind of a shadow of the sample, but on this fluorescent screen. And what I do with this is I look at defects in materials. So what I have here is 2 nanocrystals that have we fused them, kind of welded them together, but we formed a defect at that interface. So you can see each of these rows here is a row of atoms in this nanocrystal. You see there's an extra row shoved in here, and that's bad. We don't want that. Typically, these defects make things not work as well. And so we want to understand, well, how can we get rid of these defects? How do they behave in a material? And so what I do is I take videos of these defects and watch the pathways that they follow when they heal from a crystal. And so we can see here now, this interface is perfect. All the atoms, all the ducks are in a row, I like to say. And so that's what I do. And so I hope I've given you a really fun introduction and shown you what it takes to see atoms in every day, and that it has real impact for on your everyday life, even if you're not a scientist. So thank you. And when I say thank you, I mean thank you. If you're a taxpayer, which everyone is, these electron microscopes are expensive. $10 million for a state-of-the-art microscope. So I say thank you because you're the ones who support all of these cool images that have come out here. And then I'm happy to take any questions now. I'll stick around at the end of this seminar. Also, if you don't have time for that, shoot me an email. Also, they put together some fun links that I put together that are really fun introductions to different aspects of electron microscopy. So yeah, thank you for coming, and I hope you enjoyed it.
So it looks like we do have one question currently, which is the electron beam so powerful that it might damage a biological sample such as protein?
Yes, that is one of the biggest problems, is that basically you have to use so few electrons to collect this image that it's really, really noisy. And any more and you do damage it. But the detectors, the cameras that these structural biologists use are so sensitive that we can use so few electrons that we don't damage the sample and still collect enough signal to create these amazing reconstructions that you've seen. But yeah, it's a great question.
Okay, it looks like there currently aren't any more open questions either on the Zoom chat or in Facebook message. So I think Justin will be sticking around for a few minutes after the end of Sarina's talk as well. So if any questions come up in the meantime, please feel free to hang on to them and we can come back around to them after Sarina's talk. But Sarina, if you would like to share your screen, I think we can get started on your presentation. And so just as background for everybody in attendance, Sarina is currently a PhD student in the seismology lab at UC Berkeley, and she's working on how seismic data collected by a cell phone app can actually be used to improve public safety through uses such as building monitoring, for damage and tracking earthquake safety. But she decided to run down the track of earthquakes because she loves things that go boom. And she lived in New Zealand for 6 months after the severe Christchurch earthquakes, which showed her that it is very apparent that there's a lot more to learn about earthquakes and more to be done to make sure that communities can navigate these safely. She loves putting science to work and really working on her science communication, and has found research to involve a lot more steady collaborative updates to understanding rather than just working singularly. So she's going to share her data and work with you now.
Thank you very much for having me and for that introduction. So I am going to focus less on my research and try to give sort of a general status update on what's possible in terms of earthquake prediction, forecasting, and early warning. And then I'll tie back into sort of where I fit into this larger microcosm at the end. So we're going to start with prediction. And I think everyone has probably heard or even experienced the idea that maybe animals can predict earthquakes. This is a really common thing. And it's based on a kind of a understandable intuition that animals do have instincts that exceed beyond our understanding. And maybe it's possible that they could predict earthquakes. And scientists have taken this concept seriously. They have studied animal behavior and the occurrence of earthquakes. And they have unfortunately found that there is no correlation between animal behavior and earthquakes. So if animals can predict earthquakes, they're not telling us. However, what is possible and what has been observed is that animals sometimes feel earthquake vibrations sooner than people. So if you are sitting in your living room and you have a dog and the dog is lying on the floor and you're minding your own business and all of a sudden the dog starts to bark or whine or run around, and then a few seconds later you feel shaking, it would be really logical at that point to go, my God, my dog is a genius. But what's actually happening is based on the physics of earthquakes. So earthquakes are the stress building up on a fault And at a certain point, that stress exceeds the strength of the bond, this friction holding that fault in place, and the fault moves. And the release of all of that stress comes in the form of energy, which are termed seismic waves. And there are different waves that move at different speeds. And the fastest wave is termed the primary wave, the P wave. And that's associated with actually a fairly subtle vibration, one that often goes beneath the notice of humans, but can be felt by an animal, especially one that's lying on the ground. And then the secondary wave, the one that comes afterwards, is this shearing motion, and that is quite violent, and that is often what's responsible for damage in major earthquakes. And so the perception will be that for no apparent reason, an animal starts to behave very oddly, and then an earthquake occurs. But what's happening is that they're simply detecting that earthquake sooner than you can. So unfortunately, animals cannot predict earthquakes. And I swear to you that if the USGS thought they could, they would be running a kennel. The second form of earthquake prediction are the people who say that they can. And the most popular of these is probably earthquakeprediction.com. This is text that is copied from their website. They begin off by saying they are not associated with the United States Geologic Survey, and I would like to say the United States Geologic Survey is not associated with them. But they list some of the scientific methods that they use to produce their predictions, and some of these are actually what scientists use to study earthquakes, like microearthquakes and seismic gaps. And a lot of these are things that scientists have found have no correlation to earthquake behavior or physically don't make sense to how earthquakes behave. So this is, for example, like animal behavior. We have found that this does not correlate to earthquakes behave. And the second form of people saying that they can predict earthquakes are sort of popular figures. So this is one example. This is Dr. Browning. He was a meteorologist who in 1990 predicted a pretty major earthquake and caused quite a panic. And he said that he could predict this earthquake based on the alignment of planets and the moon. He said that they were all going to line up in one line. It was going to create this gravity anomaly that was going to cause all of a ruckus on Earth. And people who study the physics of Earth and gravity would be able to tell you that no alignment of planets that are millions of miles away is going to have a greater effect than the moon does on a daily basis, creating the tides. And we do not have a cascade of major earthquakes every time the tide comes in. But to the untrained ear, people who use pseudoscience, so what sounds like realistic scientific explanations, can produce predictions. And these predictions become famous and they propagate because people are really anxious, reasonably, about earthquakes, these catastrophic things that can break everything. And they want to have a semblance of control, and predictions give you that sense of control. And scientists are not immune to wanting to predict earthquakes. We could do an amazing amount of like community safety if we were capable of predicting earthquakes. And so we've given it a good college try. So here's an example in China. In 1975, they observed that there was this cluster of small earthquakes that occurred on a fault in February. And they thought maybe this means that this fault is gearing up to have something really major. So they predicted an earthquake was imminent. They evacuated the area, and 9 hours later, there was in fact a really significant earthquake, a magnitude 7, that damaged a lot of buildings, but nobody died because they had evacuated. So they were like, great, we figured it out. And the next year they tried again. They found another cluster of these small earthquakes. They thought an earthquake is imminent. They ordered an evacuation. People slept in tents outdoors for like 2 months, but no earthquake occurred. This swarm of earthquakes was not a foreshadow of a major earthquake to come. However, the month before, in a different part of China, there was no swarm, there was no forewarning, and there was a really significant earthquake that killed 250,000 people. This is considered to be one of the deadliest earthquakes in human history. So because the observables were not consistent, we consider this a prediction failure. Because when you fail to get a prediction correct, or you fail to make a prediction, people die. So China has had mixed success. We have all had mixed success. And this comes down to the definition of a useful prediction. So I could tell you right now, there's going to be an earthquake, and there will be an earthquake. There could be a small one, there could be a big one, it could be over here, it could be in Japan. That's not useful to tell you that there's going to be an earthquake. What is useful is to give you a fixed amount of time when that earthquake is going to occur, and an area when that earthquake is going to occur, like under San Francisco, and a magnitude range, because that determines sort of what kind of preparations are necessary. And you also need to provide the likelihood that this earthquake is going to occur, and it needs to be greater than the likelihood that this earthquake would occur just randomly. And in order for these predictions to be useful, they have to be a silver bullet. We need something that we can observe every time that an earthquake is going to happen. And we've tried all kinds of things. We've looked at foreshocks, like in China. We've looked at the way that seismic waves behave. We've looked at how the ground moves around. We've looked at how radon gas rates emitting from the ground change with time. We've looked at how electrical conductivity changes in our water systems. We've looked at animal behavior, like you name it, we've tried it. And we have found that many of these things have occurred before an earthquake, but none of these things have been observed before every earthquake, or even a majority of them. We haven't yet found our panacea. And the reason that predicting earthquakes is so hard is because of the nature of the scientific process. You need to observe a physical process. You need to make measurements in order to take these measurements and observe the patterns that have occurred in the past and are occurring now to project forward what could happen in the future. And when it comes to earthquake ruptures, we need a number of observations. We need to know where all the faults are, every single one of the faults that is capable of an earthquake. And this is not something that we are capable of doing right now. The Ridgecrest earthquakes that happened in July 4th weekend of last year occurred on a fault that we did not know exist. It was out in the desert, it was covered in sediment, we didn't know it was there. And so we absolutely didn't know that we could expect an earthquake there. Similarly, we're thinking about the stress and the physical properties of these faults. And faults are extremely heterogeneous. They are different where I'm sitting, where you're sitting, 5 kilometers away, 6 meters away. These things, they're these surfaces that go kilometers deep in the earth that are really hard to observe, and they're bumpy, they undulate. Some of them are made of different kinds of material. Some of them have water in them, some of them don't. And it's really difficult to characterize these things with high resolution. And we don't have right now the observation capability. And some of these things, we don't even know how to get at them, even if we did have the technology to do so. And then we also need to come up with some sort of unifying theory for how earthquakes behave. And we have the basics of this, but we don't have some really key specifics. So what we don't actually know is what is the straw that breaks the camel's back, that creates this nucleation point, the starting gun for an earthquake. We know that there's stress building up, but exactly when is it going to go? We can't figure out what starts it. And then we also don't know why some earthquakes, when an earthquake starts, grow really big, whereas most of them stay pretty small. And then when an earthquake does start to grow, we don't really understand what stops that growth. Why doesn't it just rupture the whole length of the fault? So these are the kinds of questions that we need to answer. And it's really difficult to get at this answer because earthquake rupture is what's called a critical failure process. And so we know that there's this consistent buildup of stress. This is constant, but we don't know exactly when it's going to fail. And we don't know how to figure out whether that failure is going to be big or small until it's already happening. And so the analogy that I can give you is an avalanche on a pile of sand. So I'm going to show you a video, and there will be little pieces of sand that are constantly rolling down this hill. Those are the small earthquakes. But what we don't know is when is there going to be a big avalanche? What grain of sand is too much weight for this tower to hold on to that it has to now launch a huge swath of material down the side of this? And exactly how big is that avalanche going to be? It's really hard for us to predict that, and that's what's necessary to predict earthquakes. So unfortunately, seismologists all agree that right now prediction is not possible. If someone tells you they can predict earthquakes, they are lying or they're wishful thinkers. And we don't think that prediction is anywhere in our immediate future. So unfortunately, prediction is out. However, that's not to say it's all doom and gloom. We can still do, and we do have forecasts, and we do provide early warning. So let's talk about these. So USERF3, the third Uniform California Earthquake Rupture Forecast, you can think of this like a weather forecast. This is taking what we can observe, and there's a lot, and use that to create models that predict how we might expect things to behave. And because we're not really sure, we call this a forecast, because this is associated now with a probability. There's a likelihood that things are going to behave this way, depending on sort of the error margins that we've set on the models that we use. And what we do is we take a map of the faults that we do know about, that we have observed. We use physics-based models to figure out when those faults might rupture based on the amount of stress that they're accumulating. And then we also take models of how the ground responds to earthquakes to figure out how the shaking will be distributed when one of those faults does experience a major earthquake. And these forecasts are based on the history of how faults have behaved. We look at how the faults are currently moving using really high precision GPS measurements. We know some of the tectonic dynamics that are happening on a more regional scale. We can create models of how bigger earthquakes might move through a landscape based on how smaller earthquakes behaved. We have thrown the kitchen sink into these forecasts. So we do have a lot of information, and this information has all been poured into forecasts, sort of probabilities of earthquakes occurring. So this is the most recent of these reports, the third one. They come out every few years. And what I'm showing you is a map of the Bay Area portion of this. And the colored lines are major faults. And each of these colored lines has sort of a percentage in a bubble. This is talking about the likelihood that an earthquake will occur on this fault that is greater than a magnitude 6.7 sometime between now and 2043. So they picked this like roughly 30-year time frame because that's the length of a mortgage. And a lot of people are accustomed to thinking in that sort of block of time. And so the forecast for the Bay Area is that between now or 2016 and 2043, there is a 72% chance that somewhere in the Bay Area, there will be a significant earthquake. And of that, there is a 33% chance that that earthquake will occur on the Hayward Fault, which is the one that runs under the East Bay. And there's a 22% chance that that earthquake will occur on the San Andreas Fault, which is the one that runs underneath San Francisco. So this is as close to prediction as we can get. And we really specifically call these a forecast because, like the weather forecast, they are fallible. They are not perfect, and they should not be trusted as an absolute. Whereas predictions are black and white. You're right or you're wrong. Forecasts are probabilities. This is as good as we can get on figuring out how the dice is going to roll. So we got forecasts. These are publicly available, and I can share a link at the end on how you can find more information about earthquake forecasts and some of the probable things that would result if we had one of these major earthquakes. So then the last thing that I want to talk about is earthquake early warning. And the question is, what is earthquake early warning? So this is a model of an earthquake that's starting in Northern California. And as I talked about before, there are different earthquake waves, and the fastest one, the yellow band, these are the P waves radiating it away from the earthquake. And the red circle, that's the S wave radiating it away from the earthquake. And the S wave is slower than the P wave. And this orange bit that's sort of moving down the middle of the screen, this is how the fault, more and more of the fault is becoming engaged in this earthquake. And as the P wave is radiating away, it's being picked up by seismometers. Seismometers are sensing that this shaking is happening. And seismometers send this information to a central server that then computes where the earthquake is, how big it is, and then it sends a warning forward to people so that they can expect that shaking is going to occur and these red bands occur. So we've started this earthquake several seconds ago, and we have already computed that an earthquake is in progress, and we've already sent a warning forward to people in the Bay Area that they can expect shaking. And now you have time, and people who operate major systems have time to take action to make ourselves safer when the shaking actually does arrive, which is about right now.
Sarina, how long would that take in real time? So like how early would they be able to tell you that this is happening? Is it 30 minutes, 5 minutes?
It's about 5 seconds.
Okay.
So this is the actual map of where seismic stations are located. The orange ones have already been installed and the yellow ones are planned. So we're creating a really high density of sensors. Wherever an earthquake does start, we will be able to pick it up almost immediately. We will have a sensor nearby. And we're monitoring in real time. So basically, as soon as a sensor picks it up, it is received by a computer central server. So there's this detection capacity, which is these seismic sensors, and they send their data to a central algorithm. And this algorithm takes the data from all these different sensors, and it uses just 2 seconds of data from each one of these to compute that an earthquake has begun. It figures out where the earthquake is. It figures out how big that earthquake is. And if the earthquake is big enough to warrant concern, so the shake alert system, the early warning system in the United States, has a threshold of an earthquake needs to be greater than magnitude 4.5 for us to be worried about it, because that's when people start to really feel it and some damage. Damage won't occur at 4.5, but you'll feel it. And this algorithm computes, okay, an earthquake is in progress, and it sends out an alert. And then there are a bunch of alert delivery systems, which I'll talk about, that get the word out, essentially. And what we're using is the fact that now technology is such that we can send data at essentially the speed of light, whereas seismic waves travel at roughly the speed of sound. So we have a speed advantage that we have more time to, we're able to send data faster, these messages faster, and the earthquake waves themselves can travel to your location. And as a result of receiving this alert, people can take action. So the amount of alert time that you will have before an earthquake arrives depend on your distance from the earthquake. So if you're right on top of the earthquake, we cannot possibly detect that fast enough. You will feel it. But if, for example, the earthquake starts several kilometers away from you and the nearby sensors pick it up, they can create an alert that then gets sent to you, and you will have a few seconds to take protective action. And a few seconds doesn't sound like a lot, but we can actually do quite a bit with that. So the biggest thing that we're worried about when it comes to individuals is falling hazards. So in the Loma Prieta earthquake of 1989 in Santa Cruz, over half of the injuries were linked to falling. And in the Northridge earthquake of 1994, over half the injuries were attributed to things falling on people. And if everyone received a few seconds of warning, and everyone used those 2 seconds to drop down, lower their center of gravity, take cover underneath a piece of sturdy furniture and hold on to that piece of furniture so it doesn't bounce away when the shaking starts, we could reduce the injuries that result from shaking by 50%. And to put this in economic terms, the cost of injuries in the Northridge earthquake was $2 to $3 billion. This is really significant, just a few seconds of time to take protective action. The other thing that we can do with early warning is automated control. So BART for years now has been using early warning produced by Shake Alert to slow and stop their trains, because trains are less likely to derail if they're going slower. We can also use automated control to automatically shut down delicate industrial processes that could be hazardous. And we can protect data by sort of freezing servers. And then we can also prevent cascading failures through certain forms of automation. So having alarms in hospitals so that surgeons take the scalpel out of your brain, pausing elevators at the nearest floor so that you can get out and you don't get trapped. And a major problem with earthquakes in the 90s was that the garage doors would get stuck on the buildings for firehouses because the buildings would be damaged, and they couldn't get the trucks out to now deal with the secondary hazard of the fires that were started because of downed power lines or broken gas lines. So all of these things can be mitigated if you have a little bit of time to prepare. And I want to share this part now because I think where there's a lot of sort of division and it feels like no one can agree on anything. But actually, when it comes to early warning, when it comes to this particular piece of public safety, California voters overwhelmingly support the existence of an early warning system. With all of its caveats, with all of its imperfections, people want this service to exist. And overwhelmingly, people are willing to give taxpayer dollars to make it possible. And I think that I find this really reassuring that it actually is possible for people to agree sometimes on public issues. And early warning is a beautiful example of collaboration across a multitude of institutions, nonprofits, state governments, city governments, municipal utilities, the federal government, and private companies, all working together to make it possible for people to be safer in earthquakes. Like, this has been a 15-year journey that required so many different people collaborating to create this product, because all of these people were able to agree that it was worthwhile. So now the question remains, how can you get an earthquake early warning? And the app that is across the board in California where you can receive an earthquake is called MyShake. MyShake is a free app. It's available on the App Store, both for Google and for iPhone. And it was created at UC Berkeley, actually in the lab group that I'm a part of. And so I'm definitely partial to it. And we have a license from the state Shake Alert program to deliver early warnings to your personal phone. So if you download this app and you enable location services so we can figure out where you are relative to the earthquake, then you will automatically be enrolled as long as you're in California to receive early warnings when they are pushed out. The other thing that MyShake does is it has an opportunity for you to contribute your experience. You can fill out an experience report of an earthquake that you experienced, that you were in, that you felt, and then it generates these community maps. There's also some preparedness and safety information in this app, and there's an educational component where we release information about earthquakes that are occurring around the world. And the backbone of MyShake is that it was originally and continues to be a citizen science project. So it started with scientific discovery. We used observations about how earthquakes behave, and we used information about how cell phone sensors behave to create a hazard reduction product. And we used that hazard reduction product to provide benefits to people. And then we ask people then to contribute back as citizen science, and it goes around in a circle. So what I mean by this is that we use scientific discovery to understand how earthquakes propagate, and then we produced early warning. And then we give that to people along with education and awareness and preparedness methods. And then we want to foster social engagement with that information. So I talked about the experience reports. The other backbone of MyShake is that we can use cell phones themselves as seismometers. So now we're getting into what I do. So your cell phone knows if it's upright or it's sideways because it has a sensor in it called an accelerometer. And that accelerometer is very sensitive to vibration. And we have trained using an algorithm sensors in phones to be able to tell the difference between, like, I'm on a train or I just experienced an earthquake. And then we send that data back to our servers, and we can use that data, these earthquake recordings, basically low-grade seismometers, to learn more things about earthquakes. So I use it to try and see if we can detect damage in buildings based on the way that the buildings vibrate, and to see whether we could use phones in other places that can't afford seismic networks to actually do early warning, purely powered by the people who live there. So these are some of the other things that we can learn using cell phones. And it's really exciting that we could incorporate, like, just ordinary people living their lives, and when they're not using their phones, they could be used for public safety information. And we're really hoping that this network is going to grow. So if you download MyShake, not only are you getting the benefit of early warning, but you're also contributing to our ability to learn more about how earthquakes work and how we can propagate safety information about them. The other caveat that I will give is that a couple of weeks ago, Google, the company Google, has started to automatically release early warning to anyone who has an Android phone. So if you don't download MyShake and you have an Android phone, you will still receive warning. But I would like to ask that you download MyShake because it also helps with all these other things. So the summary is that we cannot predict earthquakes, but we do have a lot of information, and that information has informed forecasts. And there's a really high likelihood that a major earthquake is coming in a few years. And we are also capable of doing early warning to give you time to prepare when an earthquake does occur. So thank you for listening. And I am happy to take questions.
It looks like we do have a question in the chat. We have, does the magnitude of an earthquake decrease in a predictable manner from its epicenter? And does the shearing motion of a fault create an audible sound as it propagates?
Both of those are really good questions. So there is a sort of a linguistic thing that is sometimes a little bit tricky. So there's an earthquake has a magnitude, and that is a description of how much energy is released in total by that earthquake. So any given earthquake has a single magnitude, and it doesn't really depend on where you're located. However, there is a word intensity, and in English, plain English, that means the same thing. But in earthquake speak, magnitude is the amount of energy associated with the earthquake, whereas intensity is the experience in a different location of that earthquake. So that's the severity of the shaking and the amount of damage that it produces. So there is sort of a predictable decrease in the severity of shaking depending on your particular distance from the fault that is rupturing. And this is based on the physics of how energy propagates through the ground. So there is more severe shaking in places that are loose unconsolidated sediments. And then there's sort of a lesser degree of shaking in sort of hard rock environments. Can you iterate the second half of that question for me again?
Yeah, so the second question is, and does the shearing motion of a fault create an audible sound as it propagates?
The actual breaking of the ground can produce a sound. I don't know if I would characterize the earthquake itself as a release of sound, but you can definitely hear like things physically breaking, which does happen along fault surfaces.
You mentioned earlier that there was a fault that wasn't even known before, and I was just curious, how are faults identified? I guess like they must have been identified before without drones, but right now I imagine using drones somehow. But yeah, I was just curious about the current state of finding faults.
So there's a few different ways that we do that. One is like earthquakes occur on them, and then we can figure out that, oh, there's a fault there. The second thing is that sometimes faults can express on the surface as offsets. So you would kind of expect things to line up, like if you have layered rock. And then if that rock is actually offset, now we can figure out that there was motion there, and that line depicts where the fault is located. We can also use trenching. So if you can't necessarily see the fault on the surface, you can dig a pit and then look at the wall and try and find those offsets in the layers there. And then we can also track where faults might be based on subtle motions of the ground. So we install GPS sensors all over the place. These are really high resolution GPS sensors that are constantly checking in with a satellite. And if you have one GPS sensor that inches along this way and one that inches along that way, there's probably something in the middle that's moving. So there's a lot of different methods that we use to try and figure out where these things are.
Okay, wow, that's really cool.
If that wraps up for questions, thank you so much, Sarina and Justin, for speaking.
Oh, sorry, just one more question.
Yeah.
Oh, Madison, if you want to go for it.
Oh, yeah, sorry. A question just came up on Facebook from Ryan Lee, which is, what is the chance that an earthquake occurs somewhere that is not along a fault line?
So earthquakes always occur on a fault simply because they are the motion of faults. So it is that tectonic motion is trying to move pieces of the crust around, and where that motion gets accommodated is along these sort of interfaces where two pieces of the crust meet, and they have bumps and they have friction, and that friction stops those things from actually moving. And when you actually apply enough pressure to that, you'll overcome that friction and you can shove past those bumpy bits and release all that stress. But that can only occur where there is an interface of two pieces of thing that can move.
We also have one final question in the chat. Are there methods of earthquake prediction that are reliable within a specific geographic area?
Not that we have found so far. There is a beautiful example of attempting to do that in what's called the Parkfield experiment. So it was observed that there's a segment of the San Andreas Fault in Central California that does experience an earthquake fairly regularly for like 100 years. It was almost every 20 years ago, every 20 years or so. And they thought maybe this is a place where we could predict it based on just the regularity. And they put all kinds of instruments up. They got really excited about it. And then the earthquake didn't happen when I thought it was going to. And it didn't happen 5 years later. And it didn't happen 5 years after that. They expected it to happen in 1988. It happened in 2004. And it was smaller than they expected. And there were absolutely no precursory signs that it was going to happen. So we can observe a lot of things, but so far we just haven't found anything anywhere that has a consistent pattern.
Looks like we have another one also coming in. Is it always better to drop and hold rather than quickly run out from a building?
Yeah, so that's actually pretty regional. So in California, we've got really good seismic standards. And your house, especially like wooden frame structures, those are designed to be kind of bendy and deal with earthquakes and not fall down. So I would say that if you're in California, your best bet is to find a sturdy piece of furniture to protect yourself from the non-structural elements like lighting fixtures and fans and pictures, and trust the structure to hold itself up around you. But in other countries, like for example in Mexico, a lot of people leave buildings because the buildings are not built to withstand shaking and they will fall down. But the thing is that with earthquake early warning, especially right now, the way that we give it out, there's no like timer. We're not telling you whether you have 1 second or 10 seconds or 20 seconds, because sometimes we're not really firm on that. And if you don't have a sense of how long you have, if you're trying to run outside and you get caught when the heavy shaking happens, the shaking can be really severe. Like you won't be able to walk, it will knock you down, and you could be in a really unsafe position at that point. So what we recommend is that you just always drop cover and hold on, and don't try to leave your building. The other thing to say about that is that while the structures of buildings are seismically certified, the frame itself is not going to fall. One of the highest things that causes damage and injury is the facade of buildings falling off and windows falling out. So if you are trying to leave a building and the shaking hits, you could get smacked by a brick, and we don't really want that. So in the United States, you're safer to stay inside.
And then I have a question about kind of like forecasting capabilities. So this might come from a naive understanding of how they give a percentage. I guess it would be my understanding that they would basically say, like, from our forecast methods, we've accurately guessed, you know, with all of these parameters, this many, like this percentage of times, which means when we see these warning signs, we can be that percentage accurate that it's going to happen.
That's almost there. So it's basically that we have taken all the observations of how faults have behaved in the past and what kind of stress regime we can measure that is occurring on these faults now, and create a model for when we think these faults might fail. And then we assign a confidence interval to how likely we think that failure is within a given time range. So it's a slightly different reorganization of what you said, but it's basically using inputs to create a model and then using that model to guess the likelihood of a certain thing.
Okay, cool. So how long have we been collecting data to, I guess, build that model, and therefore, like, how confident would we be?
Yeah.
The percentage that it gives out?
We've been collecting a lot of seismic data in a really like more uniform and rigorous way since the Cold War. We actually started with global seismic monitoring to find nuclear bomb tests. And so I would say since then, we've like really started to make that effort. And in terms of the forecasts, there have been 3. They started, I think, in 2002. And they get better every time because we add more data every time. And I don't remember the exact sort of confidence intervals they put around their forecast probabilities, but it's pretty good. These probabilities are pretty good. And then it's also important to say, like, even if someone tells you there's a 90% chance of rain and it doesn't rain, there still was that 10% chance that like it wasn't going to happen. So I would say it's a really good guess, but we have no claims to perfection.
Cool. Thanks for explaining that.
Yeah.
And then we have another question coming in through the chat, which is there evidence for the thought that a series of small shakes on a fault will prevent a much larger one?
That is a really good question. And that is also one of those things that like seems really logical. So the thing to understand about earthquakes is that the magnitude scale is logarithmic. So one magnitude 4 earthquake is 10 times smaller than a magnitude 5. It is 30 times less energy released in a magnitude 4 than a magnitude 5. So if you have a really large number of 2s and 3s and 4s, you still have a long way to go to try and release the stress that could be released all at once in a magnitude 7, 8, or 9. And the other thing to understand about small earthquakes is that all of it is a release of stress, but sometimes it's also a transfer of stress. So it is possible that you could have a small earthquake on one segment and you release the stress on that part of the segment, but you accidentally transfer a little bit to the next part, and that next part could be loading up for something real big. So sometimes it can be that these smaller earthquakes are venting really tiny amounts of stress that would otherwise be accumulated in a big earthquake, but in other instances, it's actually transferring stress and making a bigger earthquake more likely.
Would that follow that kind of areas that have higher capacity for friction then, or like higher frictional force, then can basically collect a bunch of stress moved from small earthquakes in the area, and that one part of the fault is more often the epicenter for large earthquakes?
Yeah, that is definitely yeah, you're on the right track for sure. So it is possible that sort of peripheral, more easily movable pieces of the fault could be transferring a little bit of energy at their edges. And if their edges are touching a part of the fault that has a lot of frictional load, like maybe there's a big bump and that bump is really catching on something, you could be adding stress to something that will only go into catastrophic failure because it requires that much force to force that bump to move. And in places where there is a really high friction load, there's what's called high locking. So faults have sort of this continuum of how they move. In some cases, there's not a lot of friction. And so as you apply tectonic pressure, you actually get really slow slipping along that fault, and it just moves without really shaking or bothering anybody. But in other cases, you have a really lot amount of friction. So no matter how much pressure you put on there, you don't get any incremental movement. And there's also like some continuum in the middle where it's partially slipping and partially locked. And we do think that the places that are locked are of the highest risk for a major earthquake, partially because no stress has been vented. And therefore, when they do go, we expect a large amount of stress to go at once.
Okay, great. Thank you so much for answering all of our questions. I think I saw someone saying that they've already downloaded the MyShake app.
Yes.
So hopefully that's more earthquake safety awareness just by this talk. And then I think Kelsey's gonna close us out.
Yes,
Great.
Yeah. Thank you so much, Sarina, for talking, and Justin, your presentations were fantastic and absolutely a delight to listen to. And thank you, Jenna, Madison, and Oksana, the Popping the Science Bubble team, for bringing these lectures to us. We have one coming up next month in November, third Tuesday of the month. And we're so excited. Thank you folks for tuning in over Zoom and Facebook Live. If anyone wants to add anything to that, I think we're good to close up.
We're good here. Yeah. Thanks,
Okay,
Kelsey.
Great. Thank you. Have a good night.
Thank you.